So the first thing is we're going to start talking about, well, if we have a nuclear equation, it's kind of like balancing chemical equations. It's not really a reaction, it's a nuclear equation in the sense that you have a radioactive nucleus shooting out a high-speed particle. So you have some type of, radioisotope that's stabilizing. And how does it stabilize? It's shooting out a high-speed particle. Now here we have uranium-238, so the isotope of uranium-238. If you have a periodic table with you, you might as well grab that, because in lecture, I'll be referring to these elemental symbols, and you'll actually need to look up the elements based on their atomic numbers. And again, the atomic number is the smaller number, and that shows you the number of protons. So if I look on the periodic table and I look for uranium, I go to period 7, the actinide series, and I see that U, and I can see right there that the atomic number is 92. If it undergoes an alpha particle decay, so it's shooting out, and another way to write this is, a lot of times man, that's a really bad squiggle, but they'll draw the alpha symbol, and sometimes they'll just draw the alpha symbol, sometimes they'll write the 4 too, but these are used interchangeably, so just to let you know that. But when we look at an alpha decay, if they were to show this, what I want students to realize is these two numbers add up to 92, right? And then these two mass numbers add up to 238. And that's going to help you balance these equations to make sure that the number of neutrons and protons on both sides are the same. So before, when we were balancing chemical reactions, we made sure that, the number of atoms or moles were the same on each side. Now we're getting to the nucleus, so we're making sure the number of protons and neutrons are balanced. So essentially, what is an alpha decay? Well, it's a nucleus that's unstable. So what does it want to do? It wants to break down and make itself smaller to become more stable. It's too big, right? There's too many protons next to each other. So one of the things they can do is they can reduce their mass number by 4 from the initial nucleus, right? So if we look with uranium-238, my mass number is 238. And where did I get that number? Well, I have 92 protons. 238 minus 92 means I have 146 neutrons. When I undergo the alpha decay, I'm shooting out a mass number of 4. So I'm losing a 4 from this 238. And 238 minus 4 is 234. The other thing is the atomic number is decreasing by 2 from the original nucleus. So I see that in uranium, there's 92 protons. If of the mass number of 4 from the alpha particle, 2 are protons, well, then the new nucleus will have 2 less protons, and it's 90. And we'll be able to look on the periodic table and look for atomic number 90, which again is period 7 in the actinide series, right? It's in the F block on that bottom row, and we see that 90 is thorium. So that's pretty much how you do an alpha decay. It's basically an unstable nucleus, and it shoots out 1 alpha particle, and the remaining nucleus is a little more stable. Basically, it's smaller. So how do we complete, nuclear equations? So again, we have to make sure that the mass numbers, right, are the same on both sides. So if we're looking, right, californium, we see that it's 258. 1. And the new nucleus still, if I look, the 247 and the 4 still add up to 251. So basically what we're doing is on this side, we're saying 251. And then on the other side, we're saying, if I'm shooting out an alpha particle, which has a mass number of 4, what's the mass that I'm missing? And you would basically subtract, and you would say 251 minus 4 leaves me with 247. We also have to take into account the sum of the atomic numbers on both sides. So on both sides, they're 98. So for the unstable radioisotope, if it was initially 98, and then it shoots out an alpha particle, which the alpha particle's atomic number is 2, what number, right, would be 98 minus 2? And that would be the 96. And it's this number that's going to allow me to look at the periodic table, right, the atomic number, to identify the isotope that remains. We don't want to look at the mass number, because remember, all elements can have different isotopes that have different mass numbers. So the way that we identify the elemental symbol is we use that atomic number. So I'm going to have you do this, an alpha decay for radon, right? So this is what you're told, radon, okay? So you would write the elemental symbol, and we know it's the isotope 222, right? 222. And that's all they tell you, right? But they do tell you that it's an alpha decay. So what do I have to write as one of the particles on the right side from this alpha decay? What do I have to write out as one?
Helium 4-2.
Yes, you have to write the alpha particle, which is 4-2. And I'm old. I like writing HE more than the alpha symbol. I'm weird. I don't know. I just like writing HE. You don't have to. You can just write the alpha symbol, but it just helps me, okay? So one of the things we need to do is we need to look at the elemental symbol radon on the periodic table, okay? So we need to kind of find that on the periodic table and look for it. Because when we look for it, we're going to get the atomic number, right? Did anybody find it?
86.
Yes. Where did you find it?
On the periodic table.
What group? This is good review for everybody.
The group 7A.
It's 8A, right?
Oh, right.
Noble gases.
The noble gases. So why am I bringing that up? Because that's a family that we should realize that everybody wants to be like, because remember, the noble gases has their S and P blocks filled, their sublevels. So radon, right, 222, it has an atomic number of 86. So you might have to look around for it. It's in period 6, group 8A. So the hard part, I think, is finding the elemental symbol and identifying its atomic number. Now, why do we need that? We know now, right, that we have 86 on this side, and on this side, we're going to have 86 as well. So basically, 2 plus what number is 86? So you know that the new nucleus has to be what? 84, right? So now we look on the periodic table, and we're going to look 2 to the left, and 84 is polonium. And for the mass number, right, it has to add up to 222. And the mass number of an alpha particle is 4. So 4 plus what number is 222? 218. So that is basically how you do that. Oh man, I'm sorry, I covered everything. But I think you guys, you get it. I actually like writing everything out step by step. But does that make sense how we determined the new isotope from an alpha decay?
Yes.
Yeah.
Was that pretty clear? Because a lot of students struggle with this, but if you use the math, so I just want to make sure you guys are okay with the alpha decay. Okay, looks like you were. So I'll move forward because the other ones are trickier. The alpha decay is by far the easiest and kind of the friendliest. It's the one that I kind of, you know, I'll lean more towards this, but we'll keep going, okay? So how is a beta decay different? So a beta decay is, and we actually see, we use this for carbon dating, if you guys are familiar with carbon dating. One of the things with beta decay is it doesn't like its ratio of protons to neutrons, okay? So if we look at carbon 14, right? The atomic number is 6 because it has 6 protons and it has 8 neutrons. For the most part, the nucleus likes to have like a 1 to like a 1.1 ratio of protons to neutrons. So it's trying to get that. So one of the things that carbon 14 does is it takes a neutron and converts it to a proton. Okay, so it's basically going to take a neutron and convert it to a proton. So what do we see? So it's basically a neutron in the nucleus that breaks down. So you can think of it as this. Now I don't always like thinking about it like this, but this is essentially what it is. It's a neutron that, it's not a proton, right? So when I look at the atomic number, it's 0, but it does have a mass, and it goes from a neutron to a proton, and that's why they're showing hydrogen there. And hydrogen, the atomic number is 1, and the mass number is 1. Okay, so, oops. So what we notice is, you know, the mass number is 1 on this side, and I'm shooting out a proton, so the mass number to the proton is 1. So the mass to the beta particle is a 0. But then the atomic number is 0 for a neutron, and for the proton, it's 1. So for the beta particle, we have to have a -1. And why are we having a -1? It's because it's shooting out an electron. I don't always like to say it that way. What I like to say is, okay, a neutron is neutral, and it's being converted to something positive, a proton. So how does it do that? How does something neutral become positive? What does it have to lose? If you're neutral, how are you going to become positive? What do you have to lose?
An electron.
Exactly. So the -1 and the +1 come from the neutral particle. So a neutron, to become a proton, because that's basically what it's doing. You're basically getting, and I like writing it out more like this. My neutron is becoming a proton, which is positive. So what do I have to shoot out? Something negative. This is a lot easier for me than the way they do it here. That's just me, okay? So for a neutron to become a proton, I have to shoot out something negative, and that something negative is the beta particle. Now, when we're looking at the actual nuclear equation and we want to balance it, neutrons and protons have the same mass. So in a beta decay, the mass number does not change, okay? The mass number does not change. Why? Well, neutrons and protons are the same, okay? What does change is the atomic number. And why is that? One of the neutrons becomes, right? I'm losing a neutron. So I went from 8 neutrons to 7 neutrons because one of the neutrons is changing to what? A proton. So my atomic number actually increases by 1. My atomic number goes up 1. So the carbon 14 isotope becomes the nitrogen 14 isotope. But why is it nitrogen if the mass is still 14? Because the atomic number, the number of protons, has changed. And that's what dictates what the element is. So what about for carbon, 40, or potassium 42, right? If it's a beta emitter, right? So how could you do this, right? So you could have potassium 42. Are you guys with me? And what would be the atomic number for potassium? It's in period 4, group 1A, 19. So they're telling you this is a beta emitter. And again, I don't really like doing the beta emitters, but I'm going to help you out. It's 0, -1, and then they put the little E, right, which has a negative charge. And why is it 0? What doesn't change?
Mass doesn't change.
The mass doesn't change. Good. What does change is
The atomic number.
right. One of the neutrons changed into what? One of the neutrons.
An electron.
This is how I want you to think about
Proton.
it. Changed to a proton and shot out an electron. That's what this beta particle is. It's a high-speed electron shooting out of a nucleus. But, right, the reason why this is -1 is what number -1? So I want you to think of it as -1 plus what number is going to equal 19? 20. So what we're noticing in a beta decay, or a beta emitter, really, it's not really a decay, it's an emitter. A beta emitter, the mass number is the same, but the atomic number increases by 1. And if I look at the periodic table, 1 to the right of potassium, because potassium has an atomic number of 19, 1 to the right is 20, and that is your calcium. So I have it all laid out in steps for you, but I like to first kind of show you without the steps being given to you and kind of show you how I think of it. Again, a neutron, if it's a beta emitter, is becoming a proton and shooting out a negative charge. So if I'm, converting a neutron to a proton, my mass is the same, but I'm going to increase my atomic number by 1. So mass number is the same, atomic number goes up by 1. The symbol becomes, for the atomic number of 20, calcium, and I can write out the equation. Does that make sense? It's a little more challenging, I think, than the alpha decay for sure.
This makes sense.
Are there any questions?
I think so too.
Does anybody have any questions, or are you... No? Okay. All right, cool. Good. Wow, you guys are doing good. So we'll move forward. And and this is kind of where the learning check is. I'm going to sit quiet here, if you can believe that. Well, I'm going to sit quiet for about a minute, and I'm going to let you do the beta decay for cobalt 60, the isotope cobalt 60. So I'll just give you a second. And let's see if you get it right. So if you got it right, you're doing excellent. You're exactly where you need to be if you got it right. In fact, I'm impressed because a lot of people do struggle with this. So I'll break this down and then we'll take a little break before we move forward. But basically, we knew the isotope was cobalt 60. So we only knew this. This is all we knew. So I would look on the periodic table and I would have to find cobalt. And if I look in period 4, in the D block, towards the middle, I see CO as an elemental symbol. And I see that CO is between iron and nickel in 3D sublevel. And it's 27 as an atomic number. And, I know that this is a beta decay. Now, maybe you're like me. Maybe you don't like this symbol. I don't really like that symbol. I'll be honest with you. I don't like that symbol at all. I hate it. So you're like me. You do know that a beta decay is a neutron converting to a proton and shooting out a negative particle, which we call beta decay, which is really an electron. So we got this covered. But the subtraction aspect isn't as easy with the way I think of it. I'll be honest. The way I think of it doesn't help us with the subtraction or the addition like we did with the alpha decay. So what you have to remember is you're still going to have the same mass. Why? Neutrons and protons are both 1 AMU. But if that neutron converts to a proton, my atomic number has to go up 1. That's the key. The mass stays the same, the atomic number goes up 1. 28, I look 1 to the right of cobalt, and it's nickel. And then it would be easier to derive this symbol, because then it's easy to see that 0 and 28 plus what number would give me 27? A -1. Okay. It's hard for me to start with this symbol personally. So I usually do this, and then I figure out that symbol for the beta. And you'll see, I definitely do that for the positron. I really rely on that for the positron, but yeah. So are there any questions, or are we good? Because this is a great time to take a little break. So the positron, again, it's slightly different than the alpha. It's not really a decay, it's an emission. And with the positron, typically what they write is they kind of write out the beta particle with the positive. And the reason why they do that, it's pretty much the opposite of what the beta decay is. So the beta decay, again, is the neutron converting into a proton and shooting out a high-speed beta particle, which is essentially like an electron. Now, with the positron emission, it's kind of the opposite. You have a proton, okay, and it converts to a neutron. And to do that, to go from a positive charge to neutral, it has to emit a positron. So in the beta decay, we wrote, 0, -1. For the positron, you write 0, +1, okay? Because the atomic number, instead of going up, it's going to go down 1. So we'll take a look and we'll walk through to make sure that everyone's comfortable. I personally think that positron emissions are the most difficult in balancing their nuclear equations. So it's good that we had the first two under our belt and took a little break. So you can think of it again as and this should be a plus. This should be a plus. It's basically a proton converted to a neutron, and the proton has a mass of 1 and an atomic number of 1. And it's converting to a neutron, which has a mass of 1. So the mass numbers don't change, just like in the beta decay, they didn't change. But the difference, because now instead of a neutron converting to a proton, it's proton converting to a neutron, the atomic number actually, right? I'm shooting out a positron, the atomic number goes down 1 instead of up 1. So the mass number is the same, but the atomic number decreases by 1. So here's an example. We look at manganese, right? So manganese, we look at this, it has 25 protons. So 25 protons. And if the mass number is 49, what does that tell us? Well, 49 minus 25 means I have 24 neutrons, okay? And remember, I said these nuclei, they kind of like that sweet spot of 1 proton to 1.1 neutrons, okay? So what happens is one of the protons, right? One of the protons is going to actually convert to a neutron. But to do that, it has to shoot out a positive charge from the nucleus, but not lose mass. So if I'm going from a proton to a neutron, my mass is the same, but I have extra positive charge. Well, how do I shoot out that positive charge? I shoot out a positron, which is as small as electron, but it has a positive charge, but I keep my mass. So now, when I look at this, because neutrons and protons have 1 AMU mass, right? This number is the same, right? But this number goes down 1. And why is that? The proton, I have 1 less proton. So I have 24 protons. And now I've actually gained a neutron, but my mass is the same, so it doesn't show it in the symbol, but really I have now 25 neutrons. So that essentially is what happened, and I'm getting closer to that sweet spot, 1 proton to 1.1 neutrons. And then in the process, I'm shooting out this beta particle, the positron. And if I look at the atomic numbers, right, if I look, 25, right, I'm shooting out a positron, which is +1. So what number +1 is going to give me 25? That's the 24 that I see right there. But with gamma radiation, I could actually just make one up too. You guys want me to make one up?
Yeah, just for practice.
Yeah, I'll just make one up if that's okay. I don't even know if this is going to occur, but we could just punch in some numbers. Is that okay? So this might not actually occur. I'm just going to punch in some numbers. Are you guys down for that, or?
Yeah.
Yeah, why not?
Okay, so what I'll do is, and I'm making this up, I'm not saying that this is actually going to happen, but I'll tell you that nickel 59 does a positron emission. So then you guys would have to finish the rest. Right, so you'd have to complete the rest. So I just made this up. I don't even know if there is a nickel 59 isotope, and if it does do a positron emission, it's just to help you balance the nuclear equation.
I have it.
Okay. Do you guys need more time, or are you good, or?
I got it as well.
Okay. Okay, so let's have someone help me out. What's the first thing we need to do here? What's the first thing we should do?
You would use nickel with its mass and the atomic number.
Right, which you can get from the periodic table. And now, what is that atomic number? We did it earlier, but.
It's 28.
Yeah.
Oh, wow. Okay, there it is, 28. Okay, so then I know, and you don't have to write this out, but you're basically turning what? A proton into a neutron and a positron decay, right? So I don't even write this yet, right? I just focus on the new, right, isotope. So in a positron emission, just like in a beta emission, what does not change? And it says it right here.
The mass number.
So I know it's 59. But what does happen is if the proton converts to a neutron, what happens to the atomic number?
It goes down because you're emitting a positron.
Yep, so this would be a 27. So that would be cobalt 59. And then if you want to finish out this, you would write the E positive. It has no mass, but it has a positive charge, so we write the +1, because the +1 and the 27 add up to 28. Okay, good. We did another exam. I think there's more in the road. And again, on your homework, I'll be honest, I mean, I'm probably out of all the nuclear equations, the least likely to put a positron in there. Probably most likely to do alpha. But again, in the homework, you'll get more practice. So yeah, all right. Let's move to gamma. Now gamma is just basically energy, right? It's energy. So the mass number and the atomic number don't change. So the mass number and atomic, they're the same. It's the same element. It's just an unstable nucleus. And the way they show this, like with tectonium, is they put a little M. I think that means like metastability. It's just it's basically not stable. So what happens is for the nuclear equation, it's the same exact element. Why? Atomic number doesn't change, neither does the mass, but there is an emission of gamma. So you write the gamma symbol and a 0, 0. Now why 0, 0? Well, remember, gamma is just electromagnetic radiation. It's a wavelength, it's light, it's a photon. So it doesn't have mass, so there's no mass, and it doesn't have a charge, no charge. So yeah, I mean, typically for a gamma radiation, you got to see that M, and then you just rewrite the radioisotope and write the symbol for gamma radiation. A lot of times what happens is during an alpha decay or a beta decay, gamma radiation is emitted as well. It's called like a coupling. So you sometimes see that. But this is an example of just a pure gamma emitter. So what are the summaries? So now that we've gone through it, you know, we can see that the alpha emitter, right? So the alpha symbol, it's basically for the new element, because you're emitting 2 neutrons and 2 protons, you're subtracting 4 from the mass number and 2 from the atomic number. So your beta emitters, right? Your beta for your new element is basically a neutron converting to a proton. And I could even write, you know, neutron, right? And it's going to a proton. So it's got to emit an electron, and that's what your beta is. So your new element, you're going to increase the atomic number by 1, but the mass number is the same. And then with the positron emitter, it's a little bit different. It's basically a proton in the nucleus converting to a neutron and shooting out a positron. And that's why they write out 0 plus 1 to show that charge, and here the -1 to show that it's a negative charge. But your new element's going to have the same mass, but I'm going to lose a proton because it's converted to a neutron, right? So I subtract 1 from the atomic number. And then the gamma emitter is basically, everything's the same. You just remove that M next to the mass number and write out your gamma. And your gamma symbol looks like that. So this is basically a summary of all those nuclear equations